A is the set of x plus 3y such that x and y are in Z. B is a set of even integers, and then we want to prove or disprove two things. One is that A is a subset of B. One is that B is a subset of A, although we know which one we're going to do because I circled it already. So this one is a disprove. This will be a counterexample. This one is a proof. Maybe I will start with the proof first because we have to think about how do you show one set is a subset of another. Well, we take an element of B. So let B be in capital B. We need to show B is in capital A. This would give us that B is a subset of A. Okay, well, as little b is in B, B is the set of even integers. There exists, let's say, a K and Z with B equals 2K. Now I need to create something of the form x plus 3y, where x and y are integers. Then I will know it's in A. So notice, well, this is what I just wrote, but we can also write this as minus k plus 3k, where k and minus k are both integers. You see, this will give me, so thus B is in A, because I wrote it exactly of the form integer plus 3 times integer. Okay, that's what it means to be in A. Therefore, B is a subset of A. So we have proved this side. Now, let's think about this one. We would like to disprove that A is a subset of B. Well, maybe I can draw a picture of a Venn diagram, what we know so far. So over here, this is going to be a side work box that will guide us into disproving that A is a subset of B. Okay, so let's draw a picture. This will be a Venn diagram. So far we have that B is a subset of A. Okay? And I will know, like in this picture, I see that A is not a subset of B, but I will know that is the case if I can find something here. So if I can find a little a, so what I need on this side to disprove, I need little a, that's in capital A, and little a is not in B. Or another way to think about it is it's in the set difference, capital A minus B. This would be a counterexample. And this would disprove A is a subset of B. So this is what I'm looking for on this side. Okay, well, I need something here. So let's just notice 1 and 2 are integers. And let's see, 5, which is 2 plus 3 times 1. This will be an element of A because I've represented this as 2 plus 3 times 1. 2 and 1 are integers. It's exactly at this form. X plus 3y, xy integers. However, 5 is not in B, as 5 is not even. Okay, so I have justified this and justified this. This is justification for my counterexample. So therefore, A is not a subset of B. Okay, and this would be here at the end of this side, and here at the end of this side is here. Here's another problem involving showing subset, and this is from an exam as follows. We define two sets. So for little a and Z, we have capital A and capital B sets. These are all integers that divide. Little a and all integers that divide, little a squared. and we want to prove A is a subset of B. Now, every time you have to prove one set is a subset of another, it always goes like this. So we let's say X in A show X in B, because it is an implication. You know, to B, A is a subset of B means X in A implies X in B. This is what it means to be a subset. Well, okay, so X is in A. There exists, let's see, a P and Z with, well, X divides A. X, P equals A. Okay, to be in the set B, well, we need that X divides A squared. And you know, what can I do here? I can just multiply both sides by A. So then we have XPA is A times A, or XPA is A squared. And what I will do here is I will group this like this. We are in great shape because here, so as PA is in Z, we have X divides A squared, or equivalently, X is in B. So thus, A is a subset of B. And this is the end of this proof. I would like to prove this about relations. So we have R as a relation on A. We want to prove our inverse equals R. Now, I will remind you that a relation is any subset of A cross A, and our inverse consists of ordered pairs, y comma x, such that xy is in R. Now, this is really a proof about sets, because look at what I'm trying to do. I am trying to prove that two sets are equal. Okay, now, how do we do that? Well, you take this set, show it's a subset here, and then you take R, show it's a subset here. This is how we show two sets are equal. Okay, so draw a line. That was reminding us of definitions. Now we may get to the proof. Okay, so the first one I will prove is maybe this. Oh, I should put this on this side. Subset in this direction because it's a little more straightforward. So we let's say AB in R. Well, then we know, I should say, what do we want to show? AB is in our inverse, okay? This is showing the subset this direction. We start with something here, show us in here. Okay. Then, well, BA is in our inverse. Well, now, this is the definition of our inverse, as I mentioned. But you see, if we apply our inverse here, we would interchange the first and second coordinates. So again, we interchange them. This would be in our inverse, okay? And this is what we want to prove in this direction. Thus, we have shown R is a subset of our inverse. Now we must do the other direction, which is this way. So we let AB in our inverse, and we need to show AB is in R. Okay, well, it's almost the same idea as the other direction. we can first unravel this. So if you are in, our inverse is a relation. If you are in its inverse, then you know, so we have BA must have come from what's underlined in blue, because AB is in its inverse, okay? And now, well, we think about R being the relation we're thinking about, and our inverse is the inverse. So we can just say we have this, and moreover, while we interchange it, it will be in R. AB is in R. Okay, this proof was not terribly hard, was it? However, one reason I wanted to do it is to show this is a subset of this, and this is a subset of this. This is how we show two sets are equal, okay? So what have we shown in this direction? We have shown this way. R inverse is a subset of R, okay? So we have subset in each direction, therefore the sets are equal. Let's do one more proof showing two sets are equal. And unlike the last problem, which was pretty straightforward and just used definitions in each direction, and both directions were almost the same, this one will take a little more thought. In particular, we will use this proposition, which we will use without proof. Okay, so here P and Q are distinct primes. A, if you look at it, it's the set of all multiples of P. B is the set of all multiples of Q. And then C is the set of all multiples of PQ. We want to prove that A intersect B is equal to C. And maybe I will put a line here. Okay. Okay, so to prove two sets are equal, just like the last one, or anytime you prove two sets are equal, we must show subset in each direction. Which one am I going to do first? Maybe on this side I will do this direction. So this is showing that C is a subset of A intersect B. So let C in C show C is in A intersect B. This will give us the subset in this direction. Now we look at C. Means there exists an integer, let's say M, with C equals MPQ. This is the definition of being in capital C. Okay, now we will get that C is in both A and B by just writing this exact thing here in a couple of ways. So notice, if we write it this way, that C is equal to MPQ and MP in Z means C like this, and this here means that Q divides C. Thus, C is in B. And then again, I will just start this exactly the same way, that C equals, but I'm going to write it different. Instead of MPQ, let's write this as MQP. And this is in Z. Both of these mean P divides C. So C is in A. Now, if you look at what we have C is in B, C is in A. Therefore, and C is in B, meaning C is in A intersect B. And this is what we want. So thus, we have shown that C, capital C, is a subset of A intersect B. Okay, now we do the other direction. This is for this way. We let maybe Y be in A intersect B. Okay, so now it's in both. This means Y is in A and Y is in B, right? That's what the intersection means. So then there exists, let's say, L and N integers with Y equals PL and Y equals QN. Okay? That's what it means to be in both A and in B. We have Y written these two different ways. Now, if you think about it, what do I need here? I want to show Y is in C. Comma, what I need to find an integer, let's say a W, with Y is PQW. This is what we need to show that Y is in C, and then we will have A intersect B as a subset of C. Now, we don't have it yet, right? We have Y is PL and Y is QN, but we do not have the W just yet. Okay, what can we do? Well, here, both of these are equal to Y, so we may set them equal. So we have PL equals QN, and as L is in Z, P divides QN. Okay, this is wonderful because we are ready to use this proposition. Look, it says if P divides a product, then P divides A or P divides B. And look what I have. I have P, which is prime, dividing a product. Okay, so by our, let's say I'll call it the fancy proposition, and I will even underline it in green so you see what I am using. Okay. It follows that P divides Q or P divides N. Now, P and Q are prime and they are distinct, so this cannot happen. P and Q are distinct primes. P does not divide Q. Thus, we may conclude that P divides N. There exists, let's say, well, I'll even match this letter. We want to find a W in Z. This is where I get it. So there exists a W in Z with PW equals N. Now, I am in really great shape because what I'm going to do is go back to this. I have Y as QN, and then I can replace N with PW. So therefore, Y, which is QN, is equal to Q times PW. And then as we see, PQ divides Y, meaning Y is N, C. Okay? Yay! So thus, A intersect B is a subset of C. Now we have shown that the two sets are equal because we showed C is a subset of A intersect B. We have shown A intersect B is a subset of C, and this completes our proof.